Hello everybody. Today we are going to talk about coherent source. It's the most important thing to have the interference pattern. There are some conditions. If you fulfill that conditions, then only you can have the interference pattern on the final screen. It is not like just any two sources, take the any two sources and you can have the interference pattern on the final screen. It is not that easy. To have an interference pattern, we should have coherent sources. And today I am going to talk about what are those coherent sources and what I mean by coherent sources and why they are that much important in producing the coherent, not in producing the interference pattern. So let's get started. First, I'll tell you what are coherent sources. You see, for like it is not just for applicable for the light waves. You can have the coherent water waves, you can have the coherent sound waves, and the phenomena of interference is just it is not just limited to the light waves. You can have the phenomena of interference with sound wave also, and you can have the phenomena of interference with water wave also, as I discussed in my earlier class. If you have anything that which is having the wave nature can undergo interference. I'll give you few examples, and with those things you'll get the idea and you'll get the feeling for the coherent sources. Suppose I have two sources, okay, and these two sources I'll be using for getting the interference pattern on the final screen. Suppose this is my final screen where I want to get the interference pattern due to these two sources. The first wave from this source, okay, when I can say them as coherent is that if you have the other source having the same wavelength as that of the first source, then only you can call them as coherent source. You see, from here to here it is having lambda, and this ray is also having lambda from there to there. Same wavelength, and the other thing is that in a second, in a, in a second, if this wave is going up and down two times, this wave should also undergo two oscillation, two times up and down in a second. So the condition, then only you can say them as coherent. What are those? You should have the same wavelength. The other thing is that you should have the same frequency. Indirectly, when you have the same wavelength, they will be having same frequency. So now I will tell you why you must have coherent source to have the interference pattern. Now I am trying to relate the final interference pattern with this thing. If suppose instead of having a coherent source, if you just pick any two light sources and which don't have the common wavelength among them and which don't have the same frequency, so I'll try to show you why you can't get the interference pattern with those sources. Suppose instead of having this source, I am having a source whose wavelength is bit different as compared to the first source. Now I am trying to get the interference pattern due to these two sources, S1 and S2. Now I'll tell you why I will not get the interference due to these waves. You see, whenever you are getting a dark spot on the final screen, it means what? The first source is giving you the top and the second source is giving you its bottom. Then only you can have the destructive interference. But you see, in here, when these two light rays will meet at some point, because if you have the same wavelength, they'll be having same amplitude 1 meter, suppose for example, won't possible, I'll take it as 1 nanometer, and this is also having 1 nanometer. Okay, and here I have a wave, a different thing, and here it is having let it be 0.5 nanometer amplitude. So its bottom is having same 0.5 nanometer amplitude. When they both meet destructively, it will be having 1 nanometer, and this one will be having 0.5 nanometer on the final screen. I'm talking about S1 and S2. When they both will meet on the final screen, you can't have a point on the final screen where the intensity or the light is completely vanishing. Why? Because it is half, it is the one, and here you have the half. So if they cancel each other, we have studied the principle of superposition. From that we'll add, okay, we'll add the vectors like here you have 1 and here you have 0.5, so it won't cancel out. At the end of the day, we'll be having a wave which can have the 0.5 amplitude, 0.5 nanometer amplitudes. So that's why the coherent source is important to have the interference pattern. If you don't have it, something like this will happen. You see, the source number S1 and S2 are not coherent. That's why you will not get a interference pattern on the final screen. And S1 and S2, let it be S3, they are coherent. Now if it will be 1 nanometer and this is 1 nanometer, upside this wave is having the momentum upward, and 1 nanometer, this one is having downward 1 nanometer, so they will cancel their momentas, okay, when they meet at some point. Okay, so that's how you can have a complete dark in here. Likewise, same thing applies for the bright. Same thing, same condition applies for the bright region. Okay, so that's why the coherent sources are important to have the interference pattern. Now, this is not just there are a few more properties of a coherent source, a few more things are there, and if you have those things also, then also you can say them as coherent. And what are those things? We'll check it out now. Suppose I'll always compare my other wave with my first source. Okay, now I'm gonna take another source. This source now, what I'm telling you is that the source S3, I've already taken that, so it will be S4. The source S1 and S4 both are coherent. You see, I've changed. Here, this one was starting from its top, but this S4 is starting from its bottom and S1 is starting from its top. So, I'm calling them as S1, and the S2 are also called as, they can also be coherent. How come? You see, first thing is that they both have the same wavelength. Here's you have the bottom of this, and here's also you have the bottom of this. If you compare, they both have the same wavelength. One condition got satisfied. The other thing is that same frequency. It means if this is oscillating 2 times in a second, this will also oscillate 2 times in a second. But the only thing is that between the S1 and S2, there is a phase difference of pi, 180 degrees. This wave is looking upward, and this wave is exactly looking downward. What is the phase difference between these two waves? This phase is downward and the other phase is kinda upward. So the phase difference is pi, 180 degree. So that's how that doesn't make any difference. Like they are still coherent sources. No big deal. Okay. Now one more example I'll take. S5. These two sources S1 and S4 will also produce the interference pattern on the final screen, but it will be bit different from the coherent sources S1 and S3. S1 and S3, if you use coherent sources S1 and S3 at the center on the final screen, it is sure that you are gonna get a bright spot. Why? Because when they meet, likewise top, when they meet on the final screen, so S1 and S3. Okay, due to S1 and S3, if I see the interference pattern on the final screen, at the center I'll be getting a bright spot. Why? Because they are in phase. They are in phase means exactly the same distance they will travel to reach the point O on the final screen. Same distance means if this ray is on its top, the other one, S3, will also be on its top. So that's why you are going to get a bright spot at the center. But if you take a coherent sources who is having, they are having a phase difference of pi, 180 degrees. So they both have the phase difference of pi. This one, these two sources having the phase difference of pi. In this case, in this coherent sources, you won't get a bright spot at the center. Why? Because after traveling the equal path from their sources to the point O, they will be meeting. The phase difference between them will be 180 degree, because at the start they were having the phase difference 180 degree, and at the end where they are hitting, where they are meeting at point O, there also they can have the phase difference 180 only. Why? Because they are traveling exactly same distance. When this got hit, if I take this situation, this will be on its moving upward, and this ray is moving downward. So when they meet on the final screen O, they'll be giving you destructive interference at the center on the final screen. That is what the difference is. But you will get the interference pattern. Okay. Now I'll show you one more example, and this is going to be incoherent sources. Like if you have a source from where you are getting a wave, but whose wavelength is not same, and whose wavelength is changing with time. Here's you have a bigger wavelength, and here's you have a less wavelength. So if I compare source number 1 with the source number 5th one, they are not coherent. Because what is the condition for the coherent? They should have the same wavelength. You see, this thing is not having same wavelength as this one, and the other thing is that its wavelength is keep on changing with time. So that is not allowed. So they are not coherent. If you take these two rays and try to have the interference pattern on the final screen, the same thing will happen, which got happened with S1 and S2. As I told you, you won't get any place on the final screen where you can have a destructive interference. It, like, the whole screen will be having light on it. There will be no any spot where you can have a destructive interference, because they won't cancel each other perfectly. Here's you are getting interference pattern. Okay, it's a symmetrical thing. Okay, to have a symmetrical interference, that interference pattern is a symmetry. Okay, so if you want to see that much symmetrical beautiful phenomena of light, you should send you should use waves which sources which have some symmetry between them. If you don't have the symmetry between your sources, how would you expect to get the symmetry from the interference pattern? Won't be having any symmetry. There will be interference, but that won't be sharp. Okay, now in the source S1 and S5, the other condition is that if you are getting a constant phase difference between the sources, like here as you see between S1 and S4, you are getting phase difference pi, again pi, again pi. This is at its bottom, this is at its top. Again same phase difference. Either you can have a same phase or you can have the constant phase difference between the sources. Then only you can call them as coherent. You take the example of the first and fifth source. If I take any instant, you see here's it is having zero phase difference. This is on its bottom, this one is also on its bottom. If I take a next thing, you see again you are getting zero phase difference. Why? Because on its top, again top, is the bottom of the wave. Oh my goodness, they are coming up to be same. Now if we compare the phase differences between S1 and S5, if I take this one, you see here's this ray is having it's on its top, the other one is also top, a bit later it is coming. And if I take this bottom, you see the same phase difference is not there. Here the phase difference between them is this ray is a bit ahead of this one, and here it is a bit lagging from this ray one. That's why the phase difference is there, but that phase difference is continuously not coming out to be constant. So that's where you can that's where you can't say them as coherent sources.